I would like to welcome everyone to the Isabellenhütte and CODICO webinar about the shunt-based current measurement in high voltage applications. My name is Matteo Nervo, and together with René Smogavec from Isabellenhütte, we're glad that you decided to join this webinar today. Before we start, I would like to do a short organizational overview. We will present the slides we prepared in around 45 minutes. In case you have any questions, please write them in the chat and we will go through them in our Q&A session at the end. So basically, we will present the slides in around 45 minutes and then the last 10 to 15 minutes should be for the questions. This webinar will be registered. The registration is already ongoing and you will get the slides and also the registration afterwards. Now I would like to just shortly present CODICO before we start with the presentation. CODICO stands for Component Design In Company. We stand for Design in Distribution of Active and Passive Components together with interconnect systems. CODICO is a family-owned business with around 210 employees with 43 offices in 12 countries, so basically spread all over Europe. And we stand out because we focus on the application, not only on the component itself. As to myself, I started at CODICO 3 years ago, and my current role is product manager for passive components, responsible for resistors, especially shunt resistors, and also capacitors and circuit protection devices. Part of the application focus I mentioned before is transferred also within this webinar. And together with our long-time partner, Isabellenhütte, we're glad that you decided to participate today. And as mentioned, in case you have any questions, please post them in the chat and we will answer them in our Q&A session at the end. From my side, that would be it. And René, I would like to hand over to you now.
Thank you very much, Matteo. So I plan to also give out the rules for this webinar, but I guess we already went past everything. So we're going to go through this webinar first, 45 minutes max, and then use the rest of our time for questions. So as already said in the chat, feel free to write them down there while I'm speaking, which is a bit out of the norm because I'm used to having questions right up front if there's something coming up, but I think we're going to handle that this way, the same as the other way around. So first of all, welcome everyone to this ISA and CODICO webinar about shunt-based current sensing in high voltage applications. Today we want to highlight the benefits and USPs of choosing the right current sensing component, specifically shunts, because we manufacture shunts, and also other alternatives with specific examples and product showcasing. So afterwards, you really know which one to choose, which one you need for your application, for your signal, and what to look out for. Since Matteo already introduced himself and CODICO, I probably won't go too deep into this, but we already want to thank CODICO for a great work together since 2013, so 11 years of partnership, and Isabellenhütte as a supplier supplying shunt resistors only in many different applications. We've achieved a lot across these past years. So not only high voltage applications are important, but also 12-volt automotive applications, for example, with high safety standards or strict needs and reliability. Just so you know, it's not only high voltage that we manufacture. What we wanted to say is that we were working with Matteo for a couple of years now, and we can only say this, that we really achieved a strong dynamic together and a professional and efficient work. So bottoms up for the next coming years. To myself, my name is René Smogavec, FAE at Isabellenhütte since November 22. and responsible for technical support and, let's say, product guidance for our customer base and subsidiaries for choosing the right shunt for their respective environment. And our customer base is somewhat consisting of distribution networks, key accounts, obviously, big tier ones and OEMs, but also smaller accounts all over the world. This might be enough of an introduction. And let's just go right into the presentation. So if for anyone that doesn't know Isabellenhütte while attending this webinar, we are a very old manufacturing company based in Dillenburg, Germany, which is roughly 1 hour north from Frankfurt. And we've been first mentioned in historical documents over 500 years ago that named our copper smelter at that time, where we started off with everything leading up to this moment. And is the oldest company in Hessen, which is a local state or part of Germany that you can see marked in blue on the outline of Germany here. After all these years of sourcing copper and supplying special alloys in combination with nickel and manganese, for example, we today focus on developing the most accurate analog and digital shunt-based devices for measuring electrical current with our own refined materials at hand. So meaning a high vertical integration, not getting too many pre-materials from other manufacturers. All our products are truly made in Germany, even most sub-suppliers and pre-materials. The production plants never shifted off from Dillenburg until this year, actually. We opened our production plant in China, in Changzhou, of which the opening ceremony actually took place just several weeks ago. So it's quite very fresh, and we're planning to manufacture some shunt components that are specifically targeted towards more automotive BMS and 12-volt applications. So usually welded SMD and busbar shunts. We have offices in Shanghai. We have one in the US in Boston, also a smaller one in Shenzhen, China, in Tokyo in Japan, and in Pune in India. Worldwide, we have over 1,000 employees, probably going to 1,100 more sooner or later. Group sales 206 million euro in 2024, and a bit lower than 10% of it, so 14 million euro of it went into investments such as new machinery for higher production capacity and new production lines for innovative products that were going on in our development. The company became family owned by the Häusler family 1827 and still is in 8th generation of our CFO and managing director, Dr. Felix Häusler. As we have gained deep knowledge in melting copper over the centuries, we have expanded our portfolio within the 200 years with the high precision and thermoelectric alloys. But over the last decades, we started developing a new product branches, or in this case, business units that we show, and ended with ISA's vertical deep integration. So we have the alloy department that represents the core competency of our company and also resembles the first business unit with using 2 handful of the roughly 100 alloys that we have in our portfolio nowadays. These encompass the production of our second business unit, the precision and power resistors, with high integration, and with this we have shunt resistors with carrying over the alloy USPs like stability over lifetime, low TCR, and initial tolerances in our very high-end production lines to evolve our current sensing passive components portfolio. We not only have manufactured SMD and busbar style shunts, but also THT assembly. We have some options for wire bonding or more unknown or unusual assembly types, offer special metal plating, space certification, customizability. And the third one is the business unit for sensors, highly integrated and active current sensors, shunt-based, obviously. And here we integrate our busbar shunts into the sensors to get this new business unit since 2009 that can additionally monitor voltage, insulation resistance, give additional features if needed, like a pyro fuse, and give a digital output for that. So besides these, we also have a calibrated DC meter for rated voltages up to 1,500 volts. And we already go quite into the technical side of things because we want to talk about high voltage battery management systems. Since Isabellenhütte is very fond of the automotive market, we try to stick to automotive as well because we know it the best in that way as far as we go for examples. And we can say that the importance of choosing the right physical interface in the chain of the signal chain for the BMS is the precise management is in the example of automotive BMS is the shunt or the analog interface that you choose to use for sensing the current. So the current measurement type choice determines how big your voltage drop is, what initial and total tolerance you will get, and more importantly, what kind of obstacles you're about to be faced within development because of you having high power pulses or high frequent signals. Only then you want to know what the self-inductance of your physical interface is and also work with different temperatures, probably more headroom compared to continuous RMS currents, for example. Since the shunt's standard temperature limit is at 170 degrees C, we mostly look at hotspot temperatures to mitigate problems like solder joints melting or breaking while in operation. Which is why we offer simulations for our customers with the current or emission profiles they could supply us with. Depending on the connectivity of the shunt, we can also offer shunt packages with the naked shunt only or pins or with PCB or even more developed or solutions for that. Subsequent to that, you usually need to amplify the signal you're getting from the shunt, so meaning the voltage drop, which ranges usually between 10 to 500 millivolts, meaning it's too low for direct processing of this differential signal. So usually the signal is getting filtered and converted through an ADC, and before that going through an operational amplifier to be amplified at 1 volts up to 5 volts or whichever is needed. Using the ADC, you can unlock different car functionalities by having the signal and the battery management controller or whichever microcontroller is used in this chain to be able to display the state of charge, or in this case, capacity level of the battery to know where you're at. So the shunt is a crucial component to determine how precise the percent value is that is displayed. Therefore, it's suggested to select the right one and have the lowest total error that's possible for your application. Also, in functional safety terms, according to ISO 26262, having this combination of shunt, ADC, OP, microcontroller, or battery management controller is enough for being quality managed or in the level of quality managed, but to achieve A-style ratings, C or D, usually in automotive, you will need to set safety mechanisms in place, like having error or failure diagnosis for an open shunt or drift, unusual corrosion, broken sense lines, and so on, or like redundancy to ensure reliability and a safety case according to the standard. So typically the state of health will be 100% of the time for manufacturers and will decrease over time and use. However, the battery's performance at the time of manufacturing may not meet the specification, in which case its initial state of health will be less than 100%. The biggest factors that contribute to battery degradation are driver patterns and so on. But to have the initial right accuracy, the choice is quite important, which we will getting into directly right now. So since we are speaking about high voltage, we will be speaking about busbar shunts, only because of the high currents that are going on in this sense. We have different sizes, all in metric format. Thicknesses also from roughly 1.5 millimeters to 4 millimeters, and resistance values from 20 to 500 micro. Mostly, in most cases, customers need 100 micro ohm or 20 when the nominal current really exceeds 600 amps RMS. Obviously, depending also on the terminal temperature, because with the headroom between max terminal temperature and 170 degrees, max temperature limit specified, you know how much the shunt can heat up itself to know how much current is allowed to go through to not exceed 170 degrees. So we did have a 5 micro ohm BAX shunt, but it got discontinued because we only had few inquiries coming from this variant. It has a very low voltage drop and is only feasible if you have 2,000-3,000 amps, which not many engineers really like to work with to amplify that high because of the noise that might come out of it. Similar for 500 micro ohm BAS in the middle that you see. The voltage drop is compelling and high, but if there's a need for such a value, most customers try to design in an SMD shunt, seeing their capabilities nowadays. Because for our portfolio, we have an SMD shunt going down to 100 micro ohm. So considering the material cost and space saving, not many hardware engineers nowadays probably will design busbar terminations with this and switch to the SMD solution if possible in the environment. And thicker than 4 millimeters is physically not possible because in production these kind of shunts are coiled up in the form of the alloy and copper strips. They come from our manufacturing or sub-suppliers for the electron beam welded process. The TCR is also very dependent on the resistance value because of many reasons. So if you're having a very low ohmic shunt, the resistance value is usually quite high because of the relation to the TCR that the shunt material has compared to the resistance value. It might appear very big, but there are many ways to get it low, even for low ohmic versions, which we are getting into later on. All shunts are coming with a 5% tolerance, and we have to go lower in the form of laser printing a data matrix code. There's no other way for Isabellenhütte as of today, but we will get into the solutions in a second. Since the current sensor module, what the customer is building up, needs often just 1 to 2% overall error margin, it's quite a challenge to give or supply or offer a shunt that is really fair to that requirement. So since mentioning the tolerance of the 5% initial tolerance bottleneck, more or less, this analog shunt series that I'm showing you right now, we decided to offer a more complete higher integrated solution, which is a shunt plus PCBA that has this DMC code laser printed on the shunt body, which gives us the opportunity to calibrate the resistance value for every single individual shunt and in the end of line and save it in the DMC, meaning we can achieve plus minus 0.1 to 0.2% initial tolerance, which is more reasonable for today's RFIs and RFQs. So Not all products in serial production phase. Some of them are in B and C sample phase, namely the BSL and BSX, but can be supplied as samples. As mentioned before, resistance values are very relevant in terms of which ones are getting used the most. So as you can see, we opted to only offer the 150 and 25 micro ohm because these are actually used the most. So if you have 300 amps continuous, you only need roughly 100 micro ohm, which is a good pair for the ADC and OP for the signal processing. And if it's over 600, you tend to use the 50. If it's over 1,000, it's 25. So for a functional safety reason, we use redundant measurement points that are a bit dependent on connector pin count. So for the BSL, we only have 2 measurement points. For the other ones, we have more. And for this analog shunt series, we also have 1 to 2 NTCs, thermistors, and the TCR equations and curves also saved in the DMC to gain a platform for TCR compensation, making the TCR curve way much flatter. So if you have used your AOI and scan this DMC, you're able to flatten the curve way more over the whole temperature range, which is not neutralizing the whole temperature dependency, but if you look at the dotted lines, it's more or less plus minus 0.2% for the whole range, or between -10 and roughly 65, it's even 0.1. So combined with the drift over lifetime that we often specify it at 0.5% with the shunt itself, or measure it even at around lower than 0.3, we reach a total tolerance of less than 1% without taking into account any special customer requirements or application-specific topics or exceptional environmental changes, which is very fair to offer in today's market with the high accuracy demands. Making the BSN, for example, with especially the new TCR reduction concepts that I teased you before, one of the most accurate analog shunts to date. Apart from the mere busbar portfolio that we have also smart digital CSMs or current sensor modules, active series of our shunt-based current measurement tools, with which you can use if you really are not interested in choosing your measurement points yourself with a basic busbar shunt, or want to really have a PCB press fitted in onto these pins with this high elevation over the shunt, which can be like 8 to 10 millimeters. So some don't like it because of the NTC positioning being way too high above the hotspot, or the shunt plus PCB does not appeal to you, even though you would basically just need a receptacle, so the other side of the connector. With the active modules, you have a direct connection to a CAN bus, for example, or whichever you like. For our shunt-based current measurements, we have a different portfolio for our active components, also named isoscale. And you see here all the integration levels from busbar to current sensor, from analog to active, from least BMS functionalities to many, which obviously ups the price depending on how much it is, how much functionality there is, and specifically also how customizable it's getting in the end. So you see a border between the analog and active in the middle, showing a K and small XX. At Isabellenhütte, the small X at the end most of the time initializes the size of the shunt. In this case, it's just initializing a customizable shunt or customized one. It's starting with a K always. which symbolizes our capabilities in offering the bespoke solutions, even mixing shunt-based sensing with other technologies, and even having many resistance material strips in series to have redundancy, physical redundancy, not only different measurement points on the same resistance material. So we're able to offer a lot of different solutions. And as you can see at the end, with the IVT3 Pro, which is more or less the biggest offering which we can offer for high voltage BMS environments, you not only have the current sense module, so sensing the current with our component, but also the busbar temperature, the high voltage monitoring, also an ASIL-B category, and IND, so isolation measurement, which often is replaced with a product close to the shunt, but we can integrate it into the shunt. So you don't need to invest in more components than just our one that we offer. The ICDA is one of the two isoscale products that I want to show you before we go into a big example for you, application example for choosing the right component. We have the ICD as our most compact active sensor, which is which has or features a known connector, the Tyco MCON. It features one channel current measurement at plus minus 0.5 to 0.8% reading tolerance plus offset. So depending on the measurement range in that case, of which the measurement range goes up to plus minus 500 amps. So it is also not suitable for very high currents that might occur in the environment. But it's probably 50% of what goes in RFIs or RFQs from merely the nominal current range that for me personally I hear in the daily work. It also features a temperature measurement above the shunt hotspot, directly over it to ensure a good temperature compensation. Though it finds its use in PDUs, BDUs, and charging boxes of today's world, the IVTS module does likewise in the same way, but also is used in fuel cells or USPs, transportation systems, and so on, as one of the two serial production sensors I wanted to showcase to you. It's based on a module designed to provide flexibility for fast system integration, which we pride ourselves on. So system integration for these components is quite important to us. So feel free to contact Matteo or me in that sense to get the right configuration to your component. And the feature of this shunt is a channel of current measurement in a quality managed level, 3 channels of voltage measurement, and all with CAN-bus communication, also obviously the one temperature measurement. In comparison to the ICD, the total accuracy is much lower at 0.4% reading, but with the offset of plus 0.5 amps, and 0.5% for the voltage reading. The measurement range goes up to 2,500 amps and plus minus 1,000 volts. So this is quite a wide range, which is why this one is the highest running product for our active category, and is also galvanically isolated at 1,000 volts according to ISO standards. The supply voltage can also be 24 volts instead of only 12. So going into the example, let's move on and show you the conditions that we chose for this one. We have a very simplified one, current measurement, high voltage BMS, for reading all the SO features that needed and calculation and monitored. System architecture is just centralized. microcontrol unit or the BMS performs the calculations, and current is conducted to copper bus bars, which is mostly the case. So we're focused on a bus bar shunt solution in that way. The specifications, which can be way bigger than this, but is often really sufficient for a good first offering. 450 amps continuous, 600 transient current, max 8 seconds. So more or less of a pulse load, max 8 seconds, treating it as if it's a continuous 600 amp RMS current. So nothing to calculate or simulate here. Yeah, stability over lifetime also quite normal with 0.5. Temperature headroom 15 degrees Celsius, and functional safety is also let's very basic here to give you an idea what is usually designed in. Let's start with the first one, the measurement of the if the current, what kind of options you have. Obviously, we start with the shunt because we're a shunt manufacturer. We want to push the shunt technology and give you the benefits of it. So you can measure the differential voltage between two nodes with a shunt very directly in the signal chain. You do have your power loss here because it's directly in the standing in the way of the current, but you have the most accurate voltage drop that you can read off compared to other solutions that you might get. So you can imagine to have just a voltmeter at both ends of the shunt or the shunt terminals, and get the high accuracy and flexibility of design. But then again, you have to deal with heat dissipation, like the 15 degrees Celsius that we just mentioned. You need also other components that up the total cost of ownership, and there's no galvanic isolation, which has to be handled by the other components mentioned. There are also Hall effect sensors, which is more or less the biggest contender to the shunt, due to its ease of integration, no need for much signal processing or other components for the overall design. But it's usually a bulkier product and has to deal with like parasitic effects due to the dependency of using magnetic fields like saturation and sensitivity to external magnetic fields. So generally there's a in this ceramic of the magnetic core, you have the Hall element that is supposed to output a voltage drop in that way, dependent on the electromagnetic fields that are created from the conductor, and the Hall element creates the Hall voltage that can be directly used with an ADC to further signal processing. It's cost effective, but it has its downsides, and most customers don't also have just the space of that component. There's also a closed loop version of that, which is similar in form factor but different in functions, since it relies on a compensation current that runs through a magnetic core like before until it nullifies the magnetic field that's going into the reverse direction, and is originated from the conductor that is emitted from the bus bar, for example. It is way more accurate, and this reverse current is required to counteract against the magnetic field, and it is, represents the current that is also flowing through the conductor. But it's more expensive and it's prone to the same disadvantages as the open loop. There are also different styles like the TMR, which is a sensor, a small device typically placed close to the conductor that reacts to the magnetic field also, in turn changes electrical resistance, changes the electrical resistance of the component. which is a magnetoresistive effect. The resistance value changes is then converted into a proportional voltage signal. It's small and cheap, but orientation can unfortunately lead to high tolerance variation and thus can easily be very inaccurate, which is why it's mostly just is being used as a hybrid solution in combination with, for example, a shunt. This type has been better immunity to external magnetic fields compared to Hall, but arranging several elements with different orientations can handle it, but using more also means it's more expensive and so on. There are more clever solutions to that. So all in all, we have a range of different current sensing products that you can use for the BMS. In this quick overview, you see that the correct choice technology depends on the requirements. Mostly a clear-cut answer is given because of the possible currents that occur on, with either resolution. So if there's something in the kiloamp range, 2-digit kiloamp range, shunts are not really able to work with that much. So it has to rely on a different solution. Therefore, there's rarely a gray area for both Hall effect and shunt. And most companies strictly use one because they're building up their experiences with it and get a better understanding and better accuracies out of it. So shunts do interfere with the circuit, but at the end you have a better accuracy. The size is small. If you really compare apples to apples, the cost is low. Total cost of ownership varies much if you compare the Hall sensor. The shunt in itself is cheaper, but with the other components, it's somewhat the same. But it doesn't really change the fact that you have to deal with saturation issues and possibly the parasitic effects of dealing with electromagnetic fields with the Hall effect. So going into the architectures, between the extremes, we have the centralized and the other is decentralized. In the decentralized architecture, the components communicate high quality signals in digital format to each other, such as CAN bus. In centralized, you have a sensor and actuator data signals that are processed centrally, handled and controlled by the BMU here. The BMU roughly consists of the analog front end, so the AFE, and a microcontroller, or whichever is needed to have the signal processing. Part of the analog front end is the sensor element that is feeding the AFE with an analog signal. So, for example, the shunt. Also, a important remark for these kind of architectures is that HV batteries can fail for many reasons besides punctures in the mechanical way. The service life of batteries is very dependent on electrical stress and how this is managed. And with the functionalities of the battery management unit, the BMU, the cell monitoring units, the CMU, and battery junction box, the BJB, you really have to look out for safety. And with the shunt, you can look out for safety and the right choice of it and a very accurate state of health and state of charge calculations. So the system architecture is done. We know where we stand. It's the copper bus bar. We have a continuous amp of 415. So what do? You can obviously go to the CODICO landing page and look for Isabellenhütte as one of the suppliers on the line card. And you can go to the samples that you see in the green button. And for example, choose the BSS as a sample to use for this environment, for this BMS environment that you're in. seeing that it is a 100 micron, 50 micron variant. So you go into the datasheet and you will find that we have specified the continuous current of 450 and 600 amps. So both will work for 415. So we already have our shunt, but you can also use something called the shunt overview, which we can supply afterwards to the webinar if you like. Additionally, which I like to use because it showcases all max currents, so you can just read it off there as well with all the offerings. So we also have a transient current, 600 amps, 8 seconds. If we go back to the datasheet, it's also listed there. So if you check 10 seconds, it's below 10. You have 600 and 800 amps, so it still is enough to use the 100 microohm. And obviously you try to stick with the higher ohmic one because of the higher voltage drop you can achieve with this. So less noise in the process of signal processing. Stability over lifetime is also all on the first page of the shunt datasheet. So it's specified with 0.5, even though it's very conservatively chosen. If you see our laboratory test reports, we usually go way below that. So just ask us, we can give you an external copy of that. Check on that. And the other one, which is important, is the maximum temperature of shunt hotspot. So as said, 15 degrees Celsius, we have 170 max, meaning the maximum terminal temperature must be 155 degrees Celsius hot, which gives us the 15 degrees Celsius of headroom. The 50 degrees is a sum of what the terminal temperature is and the hotspot, which is exactly in the middle of the shunt resistor. And we have a value that's called RTHI, the thermal resistance, that describes this delta. Also important is that contact resistances can be very high. So we're talking about 25 to 100 microohm. Some customers like to use nickel plating. We really try to not use nickel plating because of the hotspots that can occur on the terminal itself. So we really emphasize to using nickel tin. Also for the preservation of both surfaces. And yeah, that's why all or most components are nickel tin plated. The RTHI is listed here in the datasheet as well. So 2.0 or 1.5 Kelvin per watt is generated as the hotspot. And the calculation is as simple as the U equals R times I to calculate that. So if you have the 100 microohm, you just calculate the power that is that you get with using this resistance value and the RTHI to get the 34.4 Kelvin, which is too high because we have just 15 degrees Celsius left. With the 50 microohm, we end up with 12.9. So the result is we use the BSS analog shunt with 50 microohm. So we already have chosen the shunt, which was quite easy in this example, but we also have the functional safety aspects that are quite important for these environments. With the pin out of the BSS shunt, we can ensure functional safety with using 2 of the 4 measurement points or measurement channels that we have, with an example of using the AMC from Texas Instruments, the 23C12 here, and allocate these pins for fast responding isolated comparator and have the functional safety checked in that way. So we still need a galvanic isolation of the signal of high voltage and low voltage signal. Since it's high voltage current sensing, isolation is baked into the measurement chain itself. So the ADC is the deciding element for ensuring galvanic isolation, not a transformer or octocoupler in the typical sense. So let's choose an ADC. Using the most basic formula in electroengineering, you can calculate your voltage drop, that is the maximum voltage drop that occurs. So with our transient current, we get the 30 millivolts, and the continuous current is at 20.75. So we see with the selection of the ADCs from TI, for example, which we often refer to because it's an easy choice with a lot of good and accurate functionalities. You have either ADCs with the voltage range of plus minus 50 or 250 millivolts, so the input range, and using 250 would for max 50 millivolt input doesn't make sense for this specific example, because the AMC series shares the same resolution delta sigma 16-bit conversion within this ADCs, which means a higher effective resolution with a smaller input range, leading to better sensitivity for small currents. For realizing the SOX calculations, we have the example of using the AMC 3306. So we use the two remaining measurement pins to ensure that to have the measurement worked with in that way with an integrated OP. So on that slide, we can see the TI's schematics, which we show the needed isolation in this example. And if we zoom farther in, we see where the signal is going into the microcontrol unit, and ensuring the best noise reduction, we would really advise to use a Sync3 low-pass filter and an oversampling ratio of 256, which is mostly the highest that you can go with, and the one that results in the highest settling time, unfortunately, but it yields the highest effective number of bits for a clear signal. So this ENOP value is tied to the signal noise ratio, and thus is a good metric for the value of noise reduction. Delta sigma modulation, by the way, is a type of ADC that oversamples and noise shapes using a modulation and digital filter. So we have this example done and dusted, finished. We have our shunt and the other components. The total cost of ownership can be estimated now, and this would conclude our example in that way. For the remaining slides, we have some examples of optimizing shunt use to show you what the future might hold for even better initial tolerances or overall tolerances for you. Since we have 10 minutes left, I'll go through that quite quickly. Yeah, we will go into the questions right after. So we saw the opportunity to work with something called the current shadow that more or less is just pressure, giving the current flow the pressure of going into a different space of the cross section, just to ensure that the measurement points are isolated from the hotspot, so our TCR value is lower and our measurements are more accurate. It's what this slide basically is just saying. And there are many uses and types of doing that that are also all patented, so it's also a bit tricky to choose. Yeah, it's shifted up, so sorry, no. About TCR optimization, we already went into that. It's important to reduce the margin of error for the analysis of rest capacity of a battery. So TCR affects BMS current measurement. accuracy significantly, and we can get a better idea of the WLTP range in this automotive example, obviously. For that reason, we have investigated ways to lower the TCR, which we actually got down to 5 ppm per Kelvin for the perspective of 20 to 60 degrees Celsius, which we usually specify in the datasheet. So 50 degrees Celsius temperature rise and 50 microohm shunt, which tells in turn a change of only 0.02% of the resistance value. So your ADC is going to detect it over high temperature changes, even though it sounds very insignificant, but in the shunt world, this value is very close to neutralization of the TCR, which is a big step in this technology. In the visual interpretation of that, we have the standard manufactured shunt TCR on the left as a curve, the nominal in green, minimum and max in blue and red, without DMC compensation or TCR compensation through a data metrics code. This new TCR reduction concept seems like a monumental leap in performance, which it is, but more very important is also the big advantage of not relying on this data matrix code, that your automated optical inspection needs to scan in line, which sometimes is hard for customers. It's also a big advantage. And this scan of the DMC and use of a thermistor can come with a delay in the measurement, which you can see here. For better understanding, we have a simulation of a pulse load that is 10 seconds long. The x-axis tells the time, the y is the temperature difference between hotspot and thermistor temperature, so NTC, PTC, whatever you use. Disregarding the incoming current amplitude of 400 to 2000 amps, the generated heat that is radiating off the shunt hotspot is reaching the NTC with an inherent delay. So the NTC matches the hotspot temperature after 13 seconds and starts getting negative after 4 seconds, because the NTC temperature can keep up with the rapid cool down of the shunt hotspot. So you don't have to calculate this such delays with the thermistor, and you wouldn't even need this kind of analog shunt. So you have a very temperature stable shunt out the box. Also, something we work with at the moment is we've investigated and found feasible ways to produce busbar shunts with a mix of copper and aluminum busbars. It might be a matter of time until it's established in the market, because it can reduce a third of the copper weight when you use alloy, and almost it's a fourth of the copper price. But aluminum has lower conductivity, just 60%. So you have to consider not being able to transfer the same amount of current over the same cross section. So it's not a one-to-one replacement to the golden standard, the copper, but it's very demanded and a move forward, looking forward. Okay, I've been talking quite quickly and it was necessary, but here we are at the final slide. You can find more of about the products on both homepages of CODICO and Isabellenhütte. So feel free to either reach out to Matteo or me directly if you find necessary documents online. Else you'll find current stocks of samples, contacts, quotes, white papers, shunt selection guides even at CODICO's website, and all our data sheets, cross-reference lists if you have a different manufacturer and want to have a one-to-one cross-reference, and the ISA history, plus a download center with useful documents at some point for our new website that we just launched, respectively on both homepages. Yeah, with that said, thank you very much for listening through our today's webinar, and thanks for CODICO for this opportunity to present ISA products via their platform customer base. I hope you were able to take something from it and found it interesting. So let's jump into the questions.
Thank you, René. As always, really, really good and highly technical presentation you did. Thank you. Yeah, so we have only three minutes left. I can go on with the first question if you want. So the first question from Martin Roos is, do you have any mounting application examples for the busbar shunts? And I guess this question was done before you presented the application. So I guess we did already an application example. And I guess if it's needed, we can also provide further examples, I guess, because I have several on my folder. I guess you also have several mounting and application examples. So it could be no problem to also send it out afterwards, right?
Yes, similar to like the white papers and application reports that we have. So we have this the different kind of assembly possibilities and options for the busbar shunts. We can also talk about something very bespoke if you want to directly solder your wire onto the shunt surface or whichever. We are open for discussion, so feel free to contact us.
Perfect. Thank you. And then the next question would be, if I remember correctly, the EVTS version has been discontinued. Is that correct? And then I saw that Dennis, thank you, Dennis, already replied that the EVTS is still in our portfolio and that there is no end of this product. And I guess you mentioned it is the high runner under the sensor. So I guess this is a long-lasting project that you have.
Correct. From the product life cycle of the IVTS, it's certainly not at the end of its life, though we have the IVT Pro series that comes with a base, the IVT3 series that comes with a base and Pro variant, giving similar options, partially even improved ones, which can replace the IVTS at some point. But with everything, the whole package of the IVTS is very promising. Also, the measurement range and the isolation is just what the customer is looking for on the market. So most of our active components customers are having the IVTS and using it. There's no lookout for any end of life sooner or later.
Thank you, René. And I see this was already the last question. So for everyone, thank you really a lot for participating in this webinar. I hope you enjoyed it. And in case you have any questions afterwards, as usual, you can contact me or René or both of us, and we will try to solve whatever problem you're currently having. And as said, we have registered it, and we will send you the registration afterwards together with the slides. And yeah, René, do you want to say something else for the last words?
I think we've touched over many different topics, and thank you again for giving us the opportunity to do so. And to everyone listening, wishing you a great Wednesday.
Perfect. Then also from my side, have a nice day all, and thank you for participating.